How was the test? Yeah. All right.
Pretty good.
Yeah.
I solved the problem correctly. Only thing I was wrong. Only realized I was actually right the first time.
No, no.
And I spent the next 6 hours after the test banging myself up.
I hate that. Yeah.
But
It's hard to learn to let those things go.
I just missed it one.
Sure.
But besides that one problem, everything else actually went pretty well. The
Yeah.
practice test really
Oh,
helps.
good. Let's see.
It's just, I think the only, it's just, I think like look actually, there are a few things that he put on there that weren't on your test, but I was able to solve
Yeah.
regardless. I think like there's like one like the first problem was like a 7.3 thing.
I don't remember what section that is.
It's like the weird. I think I actually. Yeah, it's draw the graph thing.
Oh, sure, sure, sure.
I forget. It's easy. You know it's taught. You just don't know what the title of the chapter is.
Yeah.
This may be available later on your campus, right?
Yeah, of course, yeah. Oh, it's weird.
Was that for is that like something taught on Monday or
Yeah, we talked about it a little bit on Monday.
okay, yeah.
But I'm wondering this yellow border thing. Is why somebody started doing that. I don't know why. It's like it's not a huge deal. It's just kind of weird though.
Not the worst thing.
I know, but it's bothering me.
I mean, in my I think when my what are they called? It's like seven like they're like
I think it's because I'm sharing that
teachers
screen.
like one of the classes like one of the like assistant classes like top ITAs like someone put a yellow dot on the projector lens. Now everything
Yeah,
projects something just as a yellow dot.
and now it's gone. Interesting. It's because I'm sharing that screen, I guess. But I feel like that hasn't been there before. It's weird. I don't like it. Yeah. Annoying. Oh well. It's not a big deal. Should I turn off the lights? Can you see okay? Okay, cool. I'm moving on. So, for this matrix, I want to point out that finding the eigenvalues for this matrix is really, really easy. I think you should show no work when you do it because if you have a zero here or there, it's automatically going to be the diagonal elements. Let's talk about why. So, to find eigenvalues, the process is to set the determinant of your matrix minus lambda times the identity matrix equal to 0 and solve for lambda. And we'll go over this in more detail because I feel like you didn't get to see it last time, so I feel like I don't want to like be super confusing. So here's the whole process. We're just gonna take our matrix 2, 0, 5, -3. We're gonna subtract lambda times the identity matrix 1, 0, 0, 1, and we're taking the determinant of all that. Here's what always ends up happening when we're finding the eigenvalues. When you do your matrix minus lambda times the identity, what always happens is you just end up subtracting lambda from each of the diagonal entries. So this is going to end up being the determinant of this matrix. 2 minus lambda, 0, 5, -3 minus lambda. And in this case, it's super easy to solve it because when we calculate things, look what happens. We get 2 minus lambda times -3 minus lambda minus 0 times 5 equal to 0. Normally, if this part here wasn't 0, I would multiply this out. But since this part is 0, this part's essentially already factored for me. So I'm just going to leave it as 2 minus lambda times -3 minus lambda equal to 0, and then see that, oh, my solutions are lambda equal to +2 and lambda equal to -3. Typically, we call them like lambda 1 and lambda 2. It doesn't matter which one you call which. I'm going to call this one lambda 1, this one lambda 2. If you care, the convention typically is to say that lambda 1 is the bigger one, but we don't really care typically. So That's how you find the eigenvalues. Now we're going to find the eigenvectors. We'll do this again for another matrix. So now the eigenvectors. And I'll remind everybody that when we're finding eigenvectors, you're looking for a vector that when you multiply the matrix by the vector, the result still points in the same direction. So we're looking for a vector v1 such that our matrix times v1 is equal to a multiple of v1, specifically lambda 1 times v1. In this case, and I should point this is sorry, I forgot to write we're doing lambda 1 here. So for lambda 1 equal to 2, we're going to find v1 so that the matrix times v1 equals the eigenvalue times v1. So we're just going to write out the equation. So the equation is going to be our matrix A, which is 2, 0, 5, negative 3, times the vector that we're looking for. I usually call it xy, but really you can call it anything you want, equal to positive 2 times xy. I mentioned last time, but I'll say it again. Specifically when you're in a situation where your matrix is like this, where you have a 0 there or a 0 there. I should point out, this matrix is called lower triangular. And it's lower triangular because everything above the main diagonal is 0. In a similar way, so yeah, no. And if, no, I don't really want, and a matrix with a 0 down here would be called upper triangular. When this is your matrix, your eigenvectors are a little bit weirder than usual. Here's what I mean. If you look at this equations, my first equation is 2 times x plus 0 times y equals 2 times x. And while that's true, it doesn't tell us anything, right? X could literally be anything. Y could literally be anything. It's not telling me anything about the vector. And again, that's a kind of atypical situation. Let's look at the second equation. 5x minus 3y equals 2y. Oh, that's actually helpful. If I add 3y to both sides, I get 5x equal to 5y. So I get x equal to y. So the eigenvector I'm going to pick, and I will say you typically do have to choose a number. I'm going to choose x equal to 1. Usually I'm trying to choose the smallest possible integers. So I'm going to choose x equal to 1, and if x is 1, y also has to be 1. Now, this is the typical choice, but literally any multiple of that is also a valid choice. 2, 2, 3, 3, 5, 5, 7, 7, pi, pi, negative 1, negative 1. The only choice that's not a valid choice is the 0 vector. 0, 0 is never the eigenvector. Okay, it's cool. And then we'll do the same thing for the other eigenvalue. So for lambda 2 equal to negative 3, same deal. We're going to try to solve the equation a times v2 equal to lambda 2 times v2. So in this case, we're going to get, let's see, our matrix A again, 2, 0, 5, negative 3, times our vector xy. But now it's going to equal negative 3 times xy. And here, the first equation might feel not great, saying that 2x plus 0y equals negative 3x. But this equation is conclusive, meaning it's going to tell us everything we need to know about the eigenvector. So solving this, well, that goes away. 2x equals negative 3x. The only solution is what? If 2x is equal to negative 3x. What's the only number you can multiply by 2 and multiply by negative 3 and still get the same result? What's the only number you can multiply by different numbers and still get the same thing back? Not 1. 1 times 2 is 2. 1 times negative 3 is negative 3. But you're close to the right number. And split the difference. What's in between those two numbers?
2.5.
In between 1 and negative 1? Right. What's 0 times 2? What's 0 times negative 3? So 0 is the only number you can multiply by different things and still get the same result. Or you can do this the typical way, add 3x to both sides. You get 5x equal to 0 divided by 5. You get x equal to 0 divided by 5. Now, this is a really important time to remember what I said just a moment ago. The eigenvector cannot be the 0 vector. So if x is 0, y can be anything else except for 0. And we usually pick 1. So we're going to say here that my other eigenvector, v2, x is 0 and y is 1. But again, kind of like last time. So right over here, I said v1 is 1, 1, or you can pick literally any multiple of it, like 5, 5. That's a 5, believe it or not, or 7, 7. The same thing is true here. You can pick any multiple of it. So 0, 1, or 0, 6, or 0, -13. All of those are also choices for our eigenvector, which makes kind of sense, right? We just said y can be anything, and literally we could have picked y to be anything except for 0. We picked 1 because that's the normal choice.
We didn't put any other number, or is it mainly just, so maybe for a second, maybe any other number except 0? So
Well, here's kind of, here, yeah, any other number except 0. And here's kind of why. Whatever you choose for your eigenvector, another vector that points in the same direction is also a valid choice. So graphically, here's what my eigenvectors look like. My first eigenvector, v1, is 1, 1. So over 1, up 1. So there's v1. But again, any multiple of it would also work. So I could have picked 2, 2, and that would have also worked. A vector that points in the same direction is still a valid choice.
it has to be basically the same number for both.
Well, if that's your eigenvector, yes. But if your eigenvector would say like 3, 1, then 6, 2 would also be a valid choice. Right. Any non-zero multiple is also a choice. So here, if 0, 1 is your eigenvector, that means, well, my second eigenvector points straight up. But again, any vector that points in the same direction, or actually even the opposite direction, is also a valid choice. So 0, 2, 0, 7, 0, -6, all of those would be valid choices for eigenvectors. Here's why. They satisfy the equation. So if you look back at our matrix, if you take 2, 0, 5, -3, and multiply it by the vector 1, 1, we get, let's see, 2 times 1 plus 0 times 1 is 2. 5 times 1 plus -3 times 1 is 5 minus 3, which is also 2. Oh, look, we got 2 times our vector. But this would have also worked if we picked literally any other thing where they're both the same. For example, if I picked, say, -6, -6, let's see what happens. I get 2 times -6 plus 0 times -6 is -12. 5 times -6 plus -3 times -6 is -30 plus 18, which is -12. And oh, look, I got 2 times my eigenvector. They're both fitting the same role. So either one of these vectors is a valid choice, but the normal choice is to pick the vector that has the smallest possible integers. You had a question?
Vector is like not same direction, but
Well, it's a vector, it's a special vector. So for each matrix, so once you have the matrix, then each matrix usually has at least one eigenvector, usually more than that, usually as many eigenvectors as its dimension. So if it's like a 3 by 3 matrix, there's usually 3 eigenvectors. If it's a 2 by 2 matrix, there's usually 2 eigenvectors, but they're special for that matrix. So, and the eigenvector is the vector that if you multiply the matrix by the vector, you get a multiple of that vector. You get a vector that points in the same direction, or maybe the opposite direction if the eigenvalue is negative. So check it out, right? If I graph this, right? Here's my eigenvector 1, 1. And here's A times my eigenvector. So when you multiply the matrix by the eigenvector, the result still points in the same direction. And for the other eigenvector, which was 0, 1, sorry, so this is so for 2, 0, 5, -3 times 0, 1, the result's going to be 2 times 0 plus 0 times 1 is 0, and 5 times 0 plus -3 times 1 is -3. So this one, it does switch the direction, right? My initial eigenvector was pointing that way, and my matrix times the eigenvector is pointing, let's see, 1, 2, 3. There's A times V1. V2, sorry. So the matrix times the eigenvector should essentially live along the same line, right? So these vectors live on the same line, the line y equals x, and these eigenvectors live on the same line, the line x equals 0. And that's always true for eigenvectors, is that the matrix multiplied by them, you still get a vector that lives in the same line of existence. You had a question. I think you did. Okay. Cool. Yeah. And then just to say one more thing here, right? Again, just like the other one, if you were to multiply the matrix by any multiple of this eigenvector 0, 1, say like 0, -2, we're going to get 2 times 0 plus 0 times -2, which is 0. We're going to get 5 times 0 plus -3 times -2, which is positive 6. And just like this vector was -3 times the eigenvector, this vector is also -3 times the eigenvector. So again, I'm just reiterating the point that once you know an eigenvector for a matrix, any non-zero multiple of that vector is also an eigenvector with the same eigenvalue. And again, we usually pick the one with the smallest integer values if we can, but you don't have to, right? If someone asks you to find the eigenvector for this matrix, you could say 1, 1, and you could say 2, 2, and you'd both be right. Yeah, I'm going to do, yeah, I'm going to do another example here. Let's see here. Let me think for a second. Yeah. So one more kind of typical example. Let's find, yeah, I'm gonna risk it here. Find the eigenvalues for the matrix A equal to 2, 3, 1, 6. No, not 6. Do I want to do 6 there? Yeah, sure. Okay. I have no guarantee that this is going to be nice. It's probably going to be ugly because I just made a matrix. That's okay. You will encounter ugly eigenvalues. So let's do it. Determinant of A minus lambda I. So here's the work. I'm not going to show any of my work really. I'm just going to write down, I'm defining the determinant of take your matrix and subtract lambda from the diagonals. So there we got 2 minus lambda, 3, 1, 6 minus lambda. We take the determinant, that times that. So 2 minus lambda times 6 minus lambda minus that times that, 3. And then we're going to set that equal to 0. Now here, since that part there wasn't 0, which is more typical, right? That previous example was kind of atypical. We're going to multiply this out and write it as one quadratic equation. For 2 by 2 matrices, it will always be a quadratic equation. Hopefully it'll factor, but it probably won't. So let's multiply it out. Let's see what we get. So here's what I would really do. Negative lambda times negative lambda is lambda squared. Negative lambda times 6 and negative lambda times 2 is -8 lambda. And 2 times 6 is 12. 12 minus 3 is 9. I think so close. You could almost fool yourself into thinking this one factors. It does not factor. There's no good way to multiply to +9 and add up to -8. Right? I really want to say like 9 and -1 or -9 and +1, but that doesn't work. They multiply to -9. So this does not factor. So then we have to use the quadratic formula. So here our eigenvalues are going to be -8 plus or minus the square root of -8 squared minus 4 times 1 times 9, all divided by 2 times 1. So here's what we get. We get 8 plus or minus the square root of, let's see, that's 64, that's 36. 64 minus 36 is 28, I think. And we should reduce this if possible, and we can. So 28 is 4 times 7. So we have 8 plus or minus the square root of 4 times 7 all over 2, which becomes 8 plus or minus 2 root 7 all over 2. And then each part gets divided by 2, and you get 4 plus or minus the square root of 7. So those are my eigenvalues.
The thing I got lost on a few minutes, like I can where you get the 2 and 6. Where did the 3 come from? Like the matrix, the -3.
So that comes from doing this times this minus this times this.
So basically, okay, and then sorry. So
No, it's okay.
there's a few things I just kind of so basic cross multiply. I know it's like it makes up.
I did the usual determinant calculation. Upper left corner times lower right corner minus upper right corner minus lower left corner.
Like the a plus or minus is. I mean, I think the a comes from like the equation you wrote, but where does the
Right. So in this equation here, we're imagining our equation, right? This equation here, this is 1 times lambda squared minus 8 times lambda plus 9 equal to 0. So the 1, that's our a value in the quadratic formula. Our -8, that's our b value. And our 9, that's our c value. And then if it's been a minute, the quadratic formula is -b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. So I really should have written 2 times 1 down.
Yeah, that's me. I just kind of.
That's all right.
Quadratic formula.
So this definitely will come up in 17C though. Like you will need to use the quadratic formula to find some eigenvalues.
Thank you.
Especially because sometimes they will be imaginary. So if the value inside the square root here, which is called the discriminant, if that value is negative, then we're taking the square root of a negative number and we get imaginary, also called complex eigenvalues. That's not so much an issue in this class, but definitely next quarter when you take 17C, if you're taking 17C, it is something you will encounter. So just be prepared for that. And then it'll mean, so what it will mean is that if you have imaginary eigenvalues, it'll mean that your graph is a spiral. Whereas if you have real eigenvalues, your graph won't be a spiral. It'll look like something else. But that's neither here nor there. That's for later. So let's talk about how to find the eigenvectors for this not very nice eigenvalue. And I'm going to show you both ways because I do think it's worth seeing both ways. So here's the way I usually would do it. So for the eigenvectors, I would still do the usual thing, meaning I'm just trying to solve a times my eigenvector equal to lambda times my eigenvector. So in this case, let's say for lambda 1, let's say that lambda 1 is the positive one. I should say the bigger one, 4 plus the square root of 7. Our other one is 4 minus the square root of 7. Also, kind of worth noting here, are both my eigenvalues positive, both my eigenvalues negative, or do I have one positive and one negative? Well, what's 4 plus the square root of 7? Positive or negative? Definitely positive. How about 4 minus the square root of 7?
Hard to calculate about square root.
So you don't need to calculate the square root of 7. You just need to know, is it bigger than 4?
I don't think it's bigger than 4.
It's definitely not, right? It's bigger than 3 even. Or sorry, smaller than 3. Smaller than 3. Smaller than 3.
So it's still positive.
Right. So, and knowing whether your eigenvalues are both positive or one of each also is an important thing to know for next quarter because that'll be telling you whether your system is a node or whether it's a saddle. So again, things we haven't learned about yet, but knowing how to say, oh yeah, 4 minus root 7 is positive is an important skill to have. So here's how I would do it. And again, I'll preface this part with what I'm about to do is probably not the easier way to do it, which we will do in a second. So here we would say that our matrix A, 2, 3, 1, 6, times our eigenvector that we're looking for, xy, is equal to lambda 1, 4 plus the square root of 7, times our vector xy. And as usual, I'm just going to use the first equation, right? Because I'll remind you, this matrix equation is really a system of two equations, right? It's 2 times x plus 3 times y equals that times x, and it's 1 times x plus 6 times y equals that times y. And as I say this, I'm regretting that I'm going to choose that because it would be easier if I picked the 1. Let me show you what I mean. I have enough room? Yeah, I have enough room. So if I do the first equation, 2 times x plus 3 times y equals 4 plus root 7 times x. Now I have to subtract this 2x from both sides. So on the right-hand side, I'm going to write this again. I have 2x plus 3y equal to 4x plus root 7 times x. And then 4x minus 2x is going to give me 3y equal to 2x plus root 7 times x. And then I factor the x backs out. You don't really need to do that factoring. I'm just trying to show the work that's happening. You get 3y equal to 2 plus root 7 times x. And then I don't really like this next step, but I'm going to do it anyway. I'm going to say that y is equal to 2 plus root 7 over 3 times x. Now, there's a lot of different choices we can make for our eigenvector here. In my opinion, the best choice is to pick this. You can pick any non-zero number you want for x. What number do you think I might pick if I was trying to make things look less terrible for x? What's a good choice for x here?
2,
So close.
3.
Right. Why 3? Because that's going to make so I don't have a fraction. So if x is 3, then y gets to be 2 plus root 7 over 3 times 3. The 3's cancel, and you get 2 plus root 7, which I wrote kind of terribly. Sorry, I didn't mean to write so terribly there. Now, here's what I really would have done. I would have looked back a step and said, oh, yeah, remember that thing I said about how, maybe I haven't said it yet. So when you're solving this equation, it is always going to work to pick x equal to the coefficient of y and y equal to the coefficient of x, which is exactly the same choice. Yeah. Okay, I want to point something else out. And this is where, so what I really want to point out here is that people do things different ways. You're going to get answers that look pretty different, even though they're still both correct. So let's pretend like we use the second equation instead, just so you can see how that's going to look different. So if we use the second equation, we'd have, so come on, 1 times x plus 6 times y equals 4 plus root 7 times y. Okay, I'm going to show less work this time. I'm going to subtract 6y. 4y minus 6y is going to be a negative 2y. The root 7y is still going to stick around. So subtracting 6y from both sides, I'm going to get 1x equal to negative 2 plus root 7 times y. Good? So again, what I'm doing here is I'm really multiplying this out. I'm saying I have 4y plus root 7 times y. I'm subtracting the 6y to get negative 2y plus root 7 times y, and then factoring the y back out.
Yeah, I think my eye was bothering me.
Sure.
I got lost on the left side of the one x. Did you substitute the y? Did you substitute the y? You switched the y to x from?
So what I'm doing here is instead of using the first equation, 2 times x plus 3 times y equals that times x, now I'm, right, 1 times x plus 6 times y equals that times y. So now look at this. Here, if I'm going to make my eigenvector could be instead x is negative 2 plus root 7, and y is 1. 1 for y, negative 2 plus root 7 for x. And you might look at these vectors and say, those don't look like they're multiples of each other at all. But they are. There is definitely a number you can multiply this vector by to get that vector. In fact, I know what it is. It's 2 plus root 7. So don't be worried if you're working on this with someone else and they get that eigenvector, you get that eigenvector. You're both correct. It's just that this eigenvector is that one multiplied by 2 plus root 7. It's easy to see that 1 times 2 plus root 7 is 2 plus root 7. It's a little more work to see that negative 2 plus root 7 times 2 plus root 7 is in fact negative 4 plus 7, which is positive 3. Okay. Now, let me tell you the way I would actually do this one. So what I should say is both of these work just fine, but I feel like they require a little bit more algebraic manipulation. If instead you start off the other way, so instead of doing this, a times v1 equals lambda 1 times v1, we're going to do this instead. We're going to instead solve a minus lambda 1I times v1 is going to equal the 0 vector. That is the alternate equation we can solve to find the eigenvector. So let's see what happens there. So now I'm going to have my matrix. Now it's still going to be a little bit ugly because I'm subtracting my lambda 1, which is 2 plus root 7. Sorry, 4 plus root 7 from my diagonal spots. So it's going to be my matrix A, which you can't see. Here's my matrix A there. So it's going to be 2 minus 4 plus root 7, comma 3, not comma, there's no commas in matrices. 1, and then 6 minus 4 plus root 7 times the vector we're looking for, xy, equal to 0, 0. And I would simplify that matrix a little bit. So simplifying, we get 2 minus 4 is negative 2, 2, and then minus root 7. 3, 1, 6 minus 4 is 2 minus root 7. Now pick either equation. The first equation is going to give you, it's already going to have the x's and y's kind of separate for you, and there's not like an x to add to another x. So this first equation is going to be negative 2 minus root 7 times x plus 3 times y equals 0. And if you bring this over to the other side, it's going to be 3y equal to positive 2 plus root 7 times x. Oh, look, that's the equation we had before. That's going to lead us to the eigenvector v1 equal to x is 3, y is 2 plus root 7. Or if we'd chosen the second equation, our second equation is 1 times x plus 2 minus root 7 times y equals 0. And if we subtract that over to the other side, the signs change, and you get 1 times x equals negative 2 plus root 7 times y. And oh, that's going to lead us to the other eigenvector choice we talked about, which was that one right there, where where x is negative 2 plus root 7 and y is 1. So what I'm really trying to say is there's a lot of ways to do this, and you should pick the one that works best for you. I usually don't prefer doing this, but I do think, especially when the eigenvalues get really, really gross, this way is a little bit easier if your eigenvalues are not nice integer values. Yeah. Yeah.
Maybe the only I got everything on how like the top you can solve for top line and bottom values. So like the middle one, did you cross multiply again? Or
Right here.
I know the one below it.
Here. So again, like from here to here, what did I do? I just subtracted. So 2 minus 4 is negative 2, and so I'm really distributing the minus sign, right? That's a minus 4 and a minus root 7. That's a minus 4 and a minus root 7. Yep. Okay, so here's the good news. There is absolutely zero work to be done to find the other eigenvector. I'm still going to do it to show you what we get, but then I'm going to tell you what's always going to be easy about this. In fact, so I'll tell you right now, looking at this eigenvector here, my other eigenvector is going to be 3 and 2 minus root 7. Or if it was this one, it would be negative 2 minus root 7 and 1. Basically, the other eigenvector, you just change the sign of the irrational part. So whatever thing is in the radical, if it was positive square root of something, now it's going to be negative square root of something. All the radicals change. That's also true if you have complex eigenvalues. Although we don't really worry about the eigenvectors for those, so I won't actually say that. That's not so important. Let me show you. So here's actually what you could do if you wanted to be super lazy about it. Like, well, James, the other eigenvalue is 4 minus root 7. So if I go back and I just say, well, okay, if instead of a plus sign here was a minus sign here, then it would be a minus sign here, a minus sign here, and a minus sign there. Oh yeah, it just changes it. Let me show you the work though, because I feel like that's can be kind of a leap sometimes. So for the other eigenvalue, which was 2 minus root 7, so for lambda 2 equal to 2 minus root 7, I'm going to do it the first way, even though, yeah, I like the first way, yeah. So now we're trying to solve a times v2 equal to lambda 2 times v2. So that's going to be 2, 3, 1, 6, our good old matrix, times the second eigenvector. Now it's going to equal, sorry, it's not 2 minus root 7, it's 4 minus root 7. Apologies. That's my eigenvalue. Good thing I didn't mess it up yet. Cool. 4 minus root 7 times xy. And again, using the first equation, we get 2 times x plus 3 times y equals 4. I'm going to distribute the x here and say it's 4 times x minus root 7 times x. That's my first equation. And now look, subtracting 2x, we get 3y equal to 2x minus root 7 times x, or 3y equals 2 minus root 7 times x. And then that's going to lead us to the eigenvector, where x is 3 and y is 2 minus root 7. As advertised. as promised, right? It's the same eigenvector. The only thing that's changed signs is the sign of the irrational part. And that is always true. If your eigenvalues are something plus or minus the square root of something, the eigenvectors are the eigenvectors plus or minus the square root of something, right? The only thing that changes is whether the square root is positive or negative.
Make that include something square.
Oh, like if the matrix has square roots in it? That's not, I mean, that can happen. It's not very typical, but that's a good question.
Probably should expect on test or no.
I wouldn't think so. No. Most of the time our matrices have integer values or fractions at the worst.
Rational being sign
Because we plugged in the thing, we plugged in the same thing, except we just changed the sign of the irrational part. Cool. There's something else I want to say here. No, I guess not. Sure. So that's that example. I have a 3x3 example, but I feel like I don't know, it's kind of gross.
You got 15 minutes.
Yeah, let's talk about something. So let's actually do something else instead. So, oh, what was that thing? Oh, I know what it was. Yeah. So let me ask a question. So, question. If lambda equal to 0 is one of the eigenvalues of your matrix, is your matrix singular? I should really say, this is not the right, I should say, does your matrix have to be singular? That's what I really mean. So if one of your eigenvalues is 0, is your matrix having to be singular? And again, singular, what does it mean to be singular? It means it is not invertible. So as a reminder, singular means that the matrix is, so A being singular means A is not invertible. What do we know about matrices that aren't invertible? There's a very specific property we know. So if I was trying to find the inverse of A, like let's say that A was A, B, C, D. If I was trying to find the inverse of A, it'd be 1 over AD minus BC. That's the determinant of A times the other thing, D, A, negative B, negative C. What's the only situation where this thing doesn't exist? When you're dividing by, right. So A being singular, equivalently not invertible, is the same as, or is equivalent to the determinant of A being 0. So this question is really saying, if lambda equals 0 is one of your eigenvalues, is the determinant of your matrix equal to 0? Well, let's think about this. So let's look at an example, actually. So here's a really easy way to make a matrix whose determinant is equal to 0. Pick a matrix whose rows are multiples of each other. So you could say something like 2, 5, and 4, 10. I know that matrix is guaranteed to have 0 as an eigenvalue because the second row is a multiple of the first row. So let's see what happens if we find the eigenvalues. So to find the eigenvalues, determinant of our matrix minus lambda I. So let's see what we get. We get 2 minus lambda times 10 minus lambda minus 5 times 4 equal to 0. So let's see, multiplying this out, negative lambda times negative lambda is positive lambda squared. Negative lambda times 10 and negative lambda times 2 is negative 12 lambda. 2 times 10 is 20 minus 20. Oh yeah, look, the 20s cancel. We get lambda squared minus 12, lambda equal to 0. And if you factor out a lambda, you get lambda times lambda minus 12 equal to 0. So your eigenvalues are either lambda equal to 0 or lambda equal to 12. So here's what this is telling me and what it's not telling me. It is telling me that for this one matrix that isn't invertible, yeah, one of the eigenvalues was 0. What it isn't telling me yet is that's true for all matrices, right? We don't know that for any matrix whose eigenvalue is 0, that the determinant is also going to be 0. But we can prove it really quick. So here's how you would prove something like this. So we're going to assume, and let me make sure I've read the question correctly. So we're going to assume that lambda equals 0 is an eigenvalue. So assume lambda equals 0 is an eigenvalue of, sorry, brain, of the matrix A. Oh my God, A equal to A, B, C, D. All right, so here's the thing we have to remember. What does it mean to be an eigenvalue? Well, being an eigenvalue means that whatever number we have, the value is a solution to the equation determinant of A minus lambda I equals 0. That's what it means to be an eigenvalue. It means that this equation, or the previous equation, right? Right? We could have said, oh, 12 is an eigenvalue because it's a solution to the equation, determinant of 2 minus lambda, 5, 4, 10 minus lambda equal to 0. And if you plug in 12 there, it totally works. Or if you plug in 0 there, it also works. Okay, but now we're focused on the 0 part. So check it out. If lambda equal to 0 is a solution, look what's going to happen. If I plug in 0 for lambda, check it out. I get determinant of A minus 0 times I is equal to 0. But what's 0 times any matrix? In fact, let's write it out. We get determinant of A, which is A, B, C, D, minus 0 times 1, 0, 0, 1. Okay. What is this part in the parentheses really going to boil down to? The original matrix A, right? A minus all zeros is still A. So this is really just saying the determinant of A is equal to 0. But that's exactly what we wanted to show, right? Because if the determinant of A is equal to 0, that means A is singular. Not invertible, single. Okay. Seems like a good stopping place. Unless you guys want me to say more. I can say more. But we can also stop. Cool. All right. So eigenvalues, eigenvectors, definitely going to be on your final. You should practice finding them. I saw that the homework assignment that's due for section 8.7 didn't have a lot of questions on it where you actually are finding eigenvalues and eigenvectors. I would encourage you to pick some of the problems from that section and just do them. 8.7. Yeah. I think 8.6 is due. I don't remember when it's due. Okay. So for 8.7, in fact, let me just pull it up real quick here while I'm thinking about it.
For the homework yesterday.
Yeah.
Question A.
I can look at it. One sec. I have the textbook here. One moment.
You have an idea what's gonna be on the final, but you don't know.
I mean, I have a general idea like it's gonna, but no. And the problem, so the practice exams I've written are inspired by his previous midterm exams. Like I've taken his previous midterms and written practice exams are very similar to them. But I don't have any copies of his old finals. So my practice final will probably not be as directly helpful as maybe some of the other things have been. That said, I just want to grab this here. This is section 8. Yeah, section 8.7. So what was your question? Okay, let me grab it real quick. This is from 8.6, right?
I'm just gonna watch. I would like to write it down, but I'm running out of space on my notes.
Sure, that's fine.
I want to leave enough room for next week.
So is it from 8.6? Okay. One moment. Eight point six. Where are you? Okay, 8.6.
I'm just gonna. Head out.
Okay.
Thank you. Thank you. By the way, I hope you have a good Thanksgiving.
Hope you do too.
Happy
Let's
Thanksgiving.
see. So number 8.
Okay.
Oh, sure. Oh, yeah. So, yeah, this is a good. So suppose that A is non-singular. And again, all that means is the inverse exists, right? So this just means we know A has an inverse. Oh, sorry. And then the question says to prove that the inverse is unique. And typically in a math class, when you're proving something is unique, the way you do that is by assuming that it isn't. So you say, I'm going to assume that or really you say, assume that there's two of them or more, and then show that they have to be equal to each other. So I'm going to assume there's two different things and then actually show that they're the same thing. So we're going to assume that A has two inverses, B and C. And then we're going to use the definition. So the definition of being an inverse of a matrix is that when you multiply the two matrices together, what do you get? Not zero, identity. So we know that A times B and B times A must equal the identity matrix. And similarly, A times C and C times A must equal the identity matrix. For sure. That's what the definition of being an inverse means. Right? So check it out. So now we're going to start with A times B equals the identity. We're going to multiply both sides by C on the right. No, on the left, sorry. Yeah. So we're going to say that C times A times B equals C times I. What's C times I? Cool. Now on the left-hand side, matrix multiplication has what's called an associative property, meaning it doesn't matter which two you multiply together first. It's kind of like how numbers have an associative property. Like if you have 2 times 3 times 5, it's the same as 2 times 3 times 5. Because technically, you can't multiply three numbers together at once. Multiplication is what's called a binary operation, meaning you have to take two inputs and put them together. So when you have three things multiplied together, you pick which two to multiply together first, do that, and then you multiply that result by the other thing. So here, watch this. We're going to say that this is C times A times B. What's C times A? Right. What's I times B? Right. We did it. Right? We said there were two inverses, but then we showed that they had to be the same as each other. I'll say, I know it seems like it's easy the way I've done it here. That's because I've done it a lot, right? Like I know this proof I've seen before. Like it definitely takes thinking about to know like how do you approach this problem? And really, I would say not that you should focus too much on this because there's like this class really there shouldn't be too much proof writing. But the idea typically is kind of like to take what you're assuming and then kind of use the definitions we know to write down some. So like we took the fact that right, we're assuming that A has two inverses. And I said, well, what does it mean that A has an inverse? Oh, it means this and it means this. And then we tried to use that in some convenient way to show this. And I was going to look over here. So I would say, in addition to your assigned homework from section 8.7, I would really recommend looking at problems. Let's see, where do you go here? Oh, I forgot to do that. Darn. Oh, well. I would look at problem 11, not level, sure. 11A through D. 9A, 9B, 9D. That's some good practice as well. Oh, and then 13A through F. You don't have to do all of them, but like those are good. Those are problems where you're actually practicing finding the eigenvalues and eigenvectors. Yeah, it's not as bad as it sounds. So I would recommend. So I'll write it down. From section 8.7, I would recommend doing problems 11A through D, and then 12. 12 is kind of a pain, but yeah, 12 A and B. Yeah, A and B. And D. A, B, and D. And then 13 A through F. Right, 8.7. Right, 8.7? Yeah, 8.7. And again, this is really just practicing finding the eigenvalues and eigenvectors of matrices. Obviously, you're not required to do any of it, but I think some of it would be good practice.